Okay, so hello everyone. My name is Tom and here's Tammy. And today we're going to present about the Euler's identity, one of the most beautiful equations in mathematics. Before we go on to explain about the Euler's identity, we would like to talk about the applications of this identity in real life. So here I have the Schrodinger's equation, which constructs a quantum wave equation that can determine the wave function for any given situation. And it is constructed by combining cosine, imaginary number I, and the sine, which is the Euler's formula. And the real-life application of this formula is it is used in electrical engineering, signal processing, and also quantum mechanics.
To understand Euler's identity, one thing we need to understand are derivatives. The concept of derivatives comes from the concept of gradients between 2 points on a function. So let's say, for example, we were given the function x to the power of 3 minus 2x minus 1. And we chose the points a, f of a, and b, f of b. The gradient of this line here will be equal to the difference between the y values over the difference between the x values. However, let's denote the b minus a as h. However, a derivative measures the rate of change between a single point. So therefore, we need to add a limit of h. The limit of h is h approaching 0. So then we can rewrite f of b as f of a plus h. This is what a derivative is. A shortcut to derivatives is the power rule, where the derivative of f of x to the power of a is equal to a times x to the power of a minus 1. So let's say, for example, we were given the function f of x is equal to x cubed minus 2x squared. The derivative of this function will be equal to the limit of h to 0, x plus h cubed minus 2 times x plus h squared minus x cubed minus 2x squared over h. Now we can see that x plus h cubed is just x plus h multiplied by itself twice. And x plus h squared is just x plus h multiplied by itself. Here we can see that x cubed and minus x cubed cancel each other out. And 2 minus 2x squared and 2x squared also cancel each other out. So now we are only left with terms that have h in them. So now we will find terms that remain after we divided all the terms by h. So any term with, because h is approaching 0, any term with one h in them will remain in the equation, which are 3x squared h minus 2 times 2xh. We divide these terms by h, we will get the derivative of this function will be equal to 3x squared minus 4x. Here we can see that the coefficient here comes from the number of the exponential power of x. Now, Tom will differentiate sine of x and cosine of x to continue this process.
Okay, so now I will explain to you guys about the differentiations of sine x, and I will be proving it that it will be equal to the cosine of x. So we have the differentiations of sine of x, which is equal to the limit of h to 0 of sine of x plus h minus the sine of x over h, which Tammy had explained before. Now, if we want to expand the sine of x plus h, we need to use these two right triangles. So here we have the hypotenuse of the upper triangle, which is 1. So we have this side will be the hypotenuse times the sine of h. This side will be the 1 times cosine of h. Then this side will be the cosine of h times the sine of x. And this side will be the cosine of h times the cosine of x. So we can clearly see that this angle is equal to this angle. So with that, we can see that this side is sine of h, which is the hypotenuse. So this side will be the sine of h times the cosine of x. And this side will be the sine of h times the sine of x. So now we have the equation for this, which is the sine of x plus h, which is equal to this long side. So it will be equal to the sine of x cosine of h plus the sine of x cosine of h. For the cosine of x plus h, it will be equal to the lower side minus this part, which will be the cosine of h cosine of x minus the sine of h sine of x. So now I will replace this into the equation. So now we have the limit of h to 0 of sine of x cosine of h plus sine of x cosine of x and minus sine of x over h. Now I will group them outside because we have two sine of x here. So this part will be cosine of h minus 1 over h plus the sine of h over h times the cosine of x. Now Tammy will explain to you guys why the sine of h over h is equal to 1.
So now we will prove that the limit of h to 0, sine of h over h is equal to 1. To do this, I use a problem called the pizza problem, where we are given a sector of a circle with radius 1 at the origin of angle h. So if we drop an altitude from this point here to down here, this side here will be equal to sine of h. And this side, OA, will be equal to cosine of h. And if I extend OB, this side, DC, will be equal to tangent of h, because this side here is equal to 1, since it's the radius of the circle. So now we can conclude that the area of triangle OAB, which is 1/2 times cosine of h times sine of h, is smaller or equal to the area of the sector, which is pi r squared times the ratio between this angle over 360. 360 is also 2 pi, so then we can simplify this to 1/2 over h, which is smaller or equal to 1/2 tangent of h. So now let's do this quick. We can see that we can eliminate 1/2 on all sides, and then to get sine h over h, we would divide all sides by sine of h and flip the inequality. So then we will get 1 over cosine of h is larger or equal to sine h over h, which is larger or equal to cosine of h over 1. So now we will add a limit to all of these. The limit is h is approaching 0. Cosine of 0 in trigonometry is equal to 1. So therefore, the limit of h to 0, sine of h over h, is smaller or equal to 1, and it's larger or equal to 1. So therefore, this is equal to 1. Now, Tom will continue the process.
Okay, so now that we got that sine of h over h is equal to 1, we can replace it, and then we can multiply the cosine of h minus 1 over h by 1, which is cosine of h plus 1 over cosine of h, which is 1. So after we do that, we use the Pythagorean theorem, which we can get that the cosine of h minus 1 multiplied by the cosine of h plus 1, which is equal to the sine of h squared. So we will split that into two parts. And it will be equal to the limit of h to 0 of sine of x times the sine of h over h times the sine of h over cosine of h plus 1 plus the cosine of h. So it will be the limit of h to 0 of sine of x times 1 times 0 over 2 plus cosine of x, which is equal to cosine of x. So that is why the differentiations of sine of x is equal to cosine of x. Now I will do the opposite, which is the differentiations of cosine of x, and I will be trying to prove that which is equal to the negative sine of x. Okay, so with the differentiations of cosine of x, it is similar to the sine of x, but it has a little twist. So it is also equal to the cosine of x plus h minus the cosine of x over h, with the limit of h to 0, which then it will be equal to the now we wanted to expand the cosine of x plus h, which I have written here before. So we will use that and we will get the limit of h to 0 of cosine of h, cosine of x, minus the sine of h and sine of x, minus the cosine of x over h, which then we will get the limit of h to 0 and we can see clearly that this one has a cosine of x and this one also has a cosine of x. We'll put cosine of x outside and the inside will be the cosine of h minus 1 over h minus the sine of h over h times the sine of x. So I would do this quickly. So this one would be equal to 0, just like the last one. And this one will be 1 multiplied by sine of x, which this one would be equal to minus sine x. So now that I have done explaining to you guys the differentiations of cosine of x and sine of x, I would like to move on to the Taylor series. The Taylor series is a series of sum of terms, sum of infinite terms, and it is expressed as a plus bx plus cx squared plus dx cubed plus ex to the power 4 and fx to the power 5 and so on and so forth. But for the sine and the cosine graph, it has a, for the sine and for the cosine graph, it is expressed as x times x minus pi times x plus pi times x minus 2 pi times x plus 2 pi and so on and so forth. But it is also expressed as a plus bx plus cx squared plus dx cubed plus ex to the power 4 and fx to the power 5. So we can clearly see that the sine graph and the cosine graph have the product of infinite terms and also the sum of infinite terms. So it is considered a Taylor series. But what about the exponential function e to the power of x? Why does it need to be a Taylor series? This function needs to be a Taylor series because it has to keep the same value or the same function for every differentiations. So for the first differentiations, it still has to keep its function, its original function. For the second one, it's also the same. And for the third one, and so on and so forth. So it must be like an onion, but with infinite covers, because each differentiations, it will take away one term and it will degrade one exponential value. So now that we know that ex, e to the power of x, is a Taylor series, we will express it as 1. So it will be equal to a plus bx plus b, bx plus bcx squared plus dx cubed plus ex to the power 4 and fx to the power 5, and so on and so forth. So for the first differentiation, the a will turn into a 0 because it will last one term and the exponential value will degrade, so it will be b. And this is 2c, this is 3dx. 2cx and 3dx squared. For this one, it is also the same. The b would become a 0 because it takes away one term. For the t, it will lose its x, and for the d, it will lose an x too, but so it will be 3dx. For this one, it will be the c, which will be lost, and the d will lose its x. So we can clearly see that each differentiation, the values never changes. So if we replace an x with a 0, we can clearly see that every function here will turn into 1. So ex would be 1. So that means that in the first function, a would be 1. For the second function, b would be 1. For the third function, 2c would be 1, which c would be 1.5. And for the fourth one, 2 times 3d would be equal to 1, which then d would be equal to 1 over 3 factorial. And if we keep doing this, we would finally get every term of this function. And we could replace it into the function itself. So e to the power of x, the exponential function, would be equal to 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so forth. Now that I have explained about this, it's time for Tammy to introduce to you about the imaginary number and pi, and she will conclude our explanation about this Euler's identity.
So now we will want to find the coefficients in sine of x and find the pattern to the coefficients so that we can continue the process. So first we will find the differentiation of f of x, which is equal to sine of x, which will be equal to cosine of x. So then we will get 0 plus b plus 2cx plus 3dx squared plus 4ex cubed plus 5fx to the power of 4. And then we will differentiate it one more time to get the differentiation of cosine of x, which is equal to minus sine x, which is now equal to 0 plus 2c plus 2 times 3dx plus 3 times 4ex to the power of 2 plus 4 times 5fx to the power of 3. So then we will differentiate it one more time to get the derivative of minus sine of x, which is equal to minus cosine of x, which is now equal to 0 plus 0 plus 0 plus 2 times 3d plus 3 times 4ex. 2 times 3 times 4ex. And then if we do it one more time, which we will find it the derivative of minus sine x, or minus cosine of x, which is now equal to sine of x, which is now equal to 0 plus 0 plus 0 plus 0 plus 2 times 3 times 4e. So we can see here there's a pattern going on where it goes sine of x, then cosine of x, then minus sine of x, then minus cosine of x, and it starts with sine of x again. So it's a 4-cycle pattern. So now we will plug in x for 0 to find the coefficients. So if f0 will be equal to sine of 0, which is equal to 0, which will now be equal to a. F of 0 equal to cosine of 0, which is equal to 1, which is equal to b. F of 0, which is now minus sine 0, which is equal to 0, which is now equal to 2c. F of 0 equal to minus cosine of 0, which is now equal to minus 1, which is now equal to 2 times 3d. And then f of 0 equal to sine of 0, which is now equal to 0, which is equal to 2 times 3 times 4e. So from this, we can conclude that a will be equal to 0, b will be equal to 1, c will be equal to 0, d will be equal to minus 1 over 3 factorial, which is 2 times 3, and e will be equal to 0. Now we will plug these back into sine of x and cosine of x to find the series. So, if we plug these back into sine of x, it will go like this. 0 plus x, which is 1 times x, plus 0, then minus x cubed over 3 factorial, plus 0, and then following the pattern, the next term will be x to the power of 5 over 5 factorial, and then it will be plus 0 minus x to the power 7 over 7 factorial. And then cosine will, since it starts with b, the first term will be 1, and then it will be 0. Then it will be minus 2 squared, x to the power of 2 over 2 factorial, plus 0, plus x to the power of 4 over 4 factorial, plus 0, then minus x to the power of 6 over 6 factorial, and then plus 0, and goes on like that. We can see that if we compare this to e of x, which is equal to 1 plus x to the power of 2 over 2 factorial plus x to the power of 3 over 3 factorial plus x to the power of 4 over 4 factorial plus x to the power of 5 over 5 factorial plus x to the power of 6 over 6 factorial, and it goes on like that. We can see that the sum of sine of x, the sum of the Taylor series of sine of x and cosine of x are similar. However, the signs here are different. If we pull this down, we can see that there's a pattern going. It goes like positive, positive, negative, negative, positive, positive, negative, negative. So it's a four-term cycle pattern where it goes like this. So then to change this, we will use the complex number I, where I to the power of 2 is minus 1, I to the power of 3 is minus I to the power of 4 is 1. So now let's change e to the power of x a little. We change it to e to the power of I of x, which would then be equal to 1 plus ix plus, because I to the power of 2 is minus 1, this will be minus 2 minus x to the power of 2 over 2 factorial. I to the power of 3 is minus I, so then this will be minus I times x to the power of 3 over 3 factorial. I to the power of 4 is 1, so this doesn't change. Then the next term will be I times x to the power of 5 over 5 factorial. Then x to the power of 6 over 6 factorial. Then I minus I times x to the power of 7 over 7 factorial. So now we can see that the signs now match. However, the terms in sine of x are multiplied by I. So then we just need to take I times sine of x. So therefore, we can conclude that e to the power of I of x will be equal to cosine of x plus I times sine of x. So now, to conclude Euler's identity, I will plug in pi for x. So then we will have e to the power of I pi will be equal to cosine of pi plus I times sine of pi. Cosine of pi is equal to minus 1. Sine of pi is equal to 0. So therefore, I to the power of I pi, e to the power of I pi is equal to minus 1. So therefore, e to the power of I pi plus 1 will be equal to 0. And that concludes Euler's identity. Thank you for listening.